Terrestrial planet. A terrestrial planet is a small, rocky world with a solid surface. These planets are made mostly of rock and metal, and they tend to form in the inner regions of a solar system where temperatures are high. Mercury, Venus, Earth, and Mars are the terrestrial planets in our own solar system. Their surfaces can include mountains, volcanoes, valleys, and impact craters. Because they are dense and compact, terrestrial planets usually have thinner atmospheres compared to larger gas whorls. These planets are important in astronomy because they are the type most likely to resemble Earth, making them prime targets in the search for life beyond our planet. Gas giant. A gas giant is a massive planet made mostly of hydrogen and helium rather than rock. These planets form farther from their stars, where colder temperatures allow light gases to gather in huge amounts. Jupiter and Saturn are the classic examples in our solar system. Instead of a solid surface, gas giants have thick layers of clouds and storms that swirl around their atmospheres. Deep inside, the pressure becomes so intense that gases can behave like liquids or metals. Gas giants dominate their solar systems through gravity, shaping asteroid belts and influencing the paths of smaller objects. Ice giant. An ice giant is a large planet made mostly of heavier icy materials, such as water, methane, and ammonia, mixed with gases. Uranus and Neptune represent this category in our solar system. Although they are sometimes grouped with gas giants, ice giants have a different internal structure and composition. Their atmospheres often appear blue due to methane gas absorbing red light. These planets are colder and less massive than gas giants, but they still possess strong winds and complex weather systems. Ice giants help scientists understand how planets form in colder regions of planetary systems. Dwarf planet. A dwarf planet is a small world that orbits a star but does not dominate its orbital path. It has enough gravity to pull itself into a roughly round shape, yet it shares its region with other objects. Pluto is the most famous example, but others include Eris, Hame-Hame, and Makemake. Many dwarf planets are found in distant regions like the Kuiper Belt beyond Neptune. These worlds often have icy surfaces and unusual orbits. Their discovery reshaped how astronomers classify planets and revealed that the outer solar system is far more crowded than once believed. Rogue planet. A rogue planet is a planet that drifts through space without orbiting a star. These worlds likely formed in normal planetary systems, but were later ejected by gravitational interactions with larger planets or passing stars. Without a star to warm them, rogue planets are extremely cold and dark. Some may still retain internal heat or thick atmospheres that trap warmth. Astronomers detect them using subtle effects, such as gravitational lensing, where a planet bends light from distant stars. Rogue planets show that planets can exist independently of stars, wandering alone through the galaxy. Ocean planet. An ocean planet is a world where a deep global ocean covers most or all of the surface. These planets may contain enormous amounts of water, possibly hundreds of kilometers deep. Beneath the water could lie layers of high-pressure ice and a rocky core. Scientists believe ocean planets may form in regions rich in water ice and later migrate closer to their stars, where the ice melts into liquid oceans. Such planets are especially interesting in the search for life, since water is a key ingredient for biological processes. Lava planet. A lava planet is an extremely hot, rocky world where the surface is partially or completely molten. These extreme worlds orbit very close to their stars, often completing an orbit in just a few hours or days. The intense heat melts rock into vast lava oceans, and the atmosphere may contain vaporized minerals. Some lava planets may even have rain made of molten rock. These extreme conditions make them very different from any planet in our solar system, but they reveal how diverse planetary environments can be. Super-Earth. A super-Earth is a rocky planet larger than Earth but smaller than Neptune. These planets can have several times Earth's mass and may possess thicker atmospheres or stronger gravity. Super-Earths are among the most commonly discovered exoplanets around other stars. Some may be dry and rocky, while others could hold deep oceans or dense gas layers. Because of their size and potential for stable environments, scientists consider some super-Earths promising candidates when searching for habitable worlds. Mini-Neptune. A mini-Neptune is a planet smaller than Neptune, but still surrounded by a thick atmosphere of hydrogen and helium. These planets usually have a dense core of rock or ice beneath their gas envelope. They are common in other planetary systems, but do not exist in our own solar system. Many Neptunes can appear very different depending on how much gas surrounds them. Some may have cloudy atmospheres and hidden oceans beneath, while others are more gaseous. Their abundance has helped reshape modern theories about how planets grow and evolve. Carbon planet. A carbon planet is a hypothetical type of world rich in carbon instead of oxygen-based minerals like those on Earth. If such a planet forms around a star with a high carbon-to-oxygen ratio, its surface could be made of graphite, carbides, or even diamond layers. The atmosphere might contain hydrocarbons rather than water vapor. While no confirmed carbon planet has yet been found, models suggest they could exist in certain parts of the galaxy. Studying this possibility helps astronomers imagine how different planetary chemistry can become under varying cosmic conditions. Chthonian planet. A Chthonian planet is the leftover core of a former gas giant that has lost its outer atmosphere. When a gas giant orbits extremely close to its star, powerful radiation and stellar winds can slowly strip away the outer layers of gas. Over time, only the dense, rocky, or metallic core may remain. These stripped worlds provide clues about how intense stellar environments can reshape planets. They also show that planetary evolution can be far more dramatic than once assumed.